Okay, all right, so I mean, not to make this sound too terribly formal, but welcome to Topics in Spin, which is a very, very short course on angular momentum, spin, and how to understand modern physics using the concepts that we'll learn in this class. So the goals for today's lecture, which may be ambitious, are to do a brief introduction to the course itself. Then I'd like to go into a brief history of the story of spin. How many of you are familiar with the experimental and theoretical developments that really led up to spin? Okay, good. I mean, I certainly, when I was a graduate student, I didn't know any of this, and I would have appreciated some of this at the time. So I'll just give you a very, short, highly suspect overview of the history of this stuff. It's impossible to mention everybody who was involved, okay? And then finally, the big part of today will be basic math with exercises, so stuff that will be needed for the rest of the lectures in the course. I'll be the lead instructor, but I'm also expecting guest lectures from Professor Vega, and Ting Ting has actually volunteered to do a guest lecture specifically at the end on what do we expect Higgs boson decays to look like in the standard model context and a non-standard model context. What do they actually look like in a modern particle physics detector, and how do you make sense of the reconstructed experimental information in lieu of the theory that you're attempting to test? Okay, so let me kill these for a moment. I'll only have the lights off for a bit, so this will just be brief, okay? But, so the goals of the short course are to review briefly the history of spin as a concept, both from its experimental and its theoretical perspectives. Those are tightly intertwined, and one of the things I want you to take away from this introduction is that in physics, as I guess it should be obvious, but maybe it's not so obvious in the modern world, we make progress in the interplay of experiment and theory, not when only one of those is making progress. All right, so experimental observations absent theoretical explanations that can be tested, verified, expanded, and retested are really just useless. You're just observing things about the world with no explanations, which is nice, but that's not science. And theory absent experimental input is just storytelling. And there's been a lot of that going on for sort of 30 years now. And we may, it seems, finally be entering an era where we can focus on what stories are real and what stories are useless. Then I'd like to discuss the basic mathematics that's needed for the rest of these lectures. That's what we're going to do today. We'll get to angular momentum next time, both orbital and, I hope, spin. Although the toolkit you can develop from orbital angular momentum serves you very well in the spin discussion. Once you kind of mastered the basics of orbital angular momentum, you get spin for free after that. You only have to take into account the fact that it's half integer and whole integer, not just whole integer like orbital angular momentum. And most importantly, we'll talk about the addition of angular momentum and what are the implications for the total angular momentum of systems involving more than one particle. We'll discuss relativistic quantum mechanics and the role of spin in that framework. This, of course, is the correct or nearly completely correct description of nature as far as we know. The only thing that's really missing from relativistic quantum mechanics is quantization of the potentials in the theory, which once you do that, you get field theory. All right, so field theory is really the best description of nature we have. This gets us pretty close. And finally, we'll apply the concepts that we've learned to the identification of a new particle with a mass of 126 GeV. Ting Ting's working on this for her PhD thesis. She's done the work already. Once you've discovered a new particle, you have to ask, well, how do I know it's the thing I was looking for, in this case, the Higgs boson? And that's what I hope to get you to take away from that last part, something useful, something you can go both in theory and in an experiment in a modern context and do. Okay, so just some things some people have asked, are there any books I should be using for this course? Yes, all of them, but the goal of the course is to give you the material you need with hints to things you could look at more. But there's a lot of material that goes into a course like this. So these are some things that I've certainly been using to develop the course in alphabetical order by the last name of the author. It's ironic that this one shows up first. Quantum Mechanics Demystified, which is basically quantum mechanics for dummies, if you want to put not too fine a point on it. But hey, I'm an experimentalist. I get to use these things. I found it's useful, but there are mistakes. It's sloppy, so you do need to be careful. Merzbacher is a very good book on quantum mechanics, as is Shankar, Principle of Quantum Mechanics. A lot of Shankar's book is reflected in these lectures, at least at the beginning. And I also very much like Shankar's survey called Basic Training in Mathematics, a fitness program for science students. This is undergraduate level math methods of physics, but it nicely samples across the basic topics in some depth, which is useful. I really like Strang's linear algebra and its applications. The reason I like it is because it talks about physics all the time, and specifically it talks about quantum mechanics. So when it talks about things like the eigenvalue problem, when it talks about the Schwartz inequality, it does so in a way that references, hey, this is useful because in quantum mechanics you want to understand blank. And that's what I really liked about this book. It's not just math for math's sake. And then finally, one of the books I read as a postdoctoral researcher, which helped me to understand a little bit about the history of spin as a concept, is Tomonaga's The Story of Spin, which is really, it's a very good book. It's not outstanding. It glosses over some things I'd rather it not, but it gets you a pretty good picture of how spin developed as a concept, both experimental and theoretical, over many decades. Okay, so here comes the very brief and oversimplified history of spin angular momentum. Was there a question, Eric? Or no? Okay. Okay, so we have to kind of put ourselves in the 1800s. So back in the 19th century, and what was going on in the 19th century? Well, you have this new kid on the block. You have electromagnetism, codified in Maxwell's equations as a complete theory of electric and magnetic phenomena. And it had a problem, as you're probably aware, or at least it had a problem from the perspective of the much better established classical mechanics, and that was that under Galilean transformations, you predicted phenomena in electromagnetism that simply did not manifest in the laboratory. And so it seemed as if the laws of electricity and magnetism were not invariant under space-time transformations of the Galilean form. It took a lot of work to sort out what was wrong. Of course, the problem was classical mechanics. It wasn't electricity and magnetism. That was the correct theory. Classical mechanics had to be modified to get a more complete form of space-time transformations from one frame of reference into another. So, you have this churn going on experimentally and theoretically in the second half of the 1800s regarding electricity and magnetism. You also have what turns out to be the culmination of the atomic theory of matter. Right? So the existence of elements was extremely well established at this point. But the explanation of elements and compounds, so combinations of elements, was not that well established. And we take for granted now the atomic theory of matter. But in fact, it's not that old an idea, at least an established scientific explanation for the structure of matter. So we have in 1897, J.J. Thomson, establishing the existence of something called the electron, which seemed to carry the fundamental unit of electric charge established by the Millikan oil drop experiment. And this is really, although he didn't know it at the time, this is really the first discovery of what we now would think of as a subatomic particle, something that makes up an atom. As I said, that wouldn't be known until at least half a decade later. But Thomson did experiments involving, cathode ray tubes, as we would now call them, to isolate the properties of this thing, not as a wave, not a classical wave. It wasn't another wave phenomenon. It wasn't another atomic phenomenon or elemental phenomenon. It was something else. And so he did experiments that basically established that it was its own independent thing. And we can basically reproduce those experiments without doing any actual measurement by actually hooking up a cathode ray tube, which is what I'm going to do now. So it's pretty simple. You just hook one end of the cathode ray tube into a ground, so a sink for charge. And then you need a source of charge. So for that I have a handheld Tesla coil. This thing's pretty nasty. So give me a second here. This is going to make all kinds of noise. Okay. So that's busy making ozone right there. And it's on the minute you plug it in, which is why I don't like it. All right, so I'm going to hook it up to the other end. So we have basically an anode over here, a cathode over here, and with this high voltage across the tube, you can then boil electrons off the metal on one end. They pass through a slit to make a collimated beam of electrons, and you'll see that beam represented by the interaction of electrons with a phosphorescent material inside of the target wall of the tube here. So let me just go ahead and turn this on. Okay. All right, so right now you're making a beam of electrons, and if we had some magnets, you could actually steer this. So this is basically a miniature particle accelerator, and it takes no effort to make one of these. So it takes effort in controlling one of these. All right, so Thomson experimented a great deal with equipment like this, using what he had at the time to establish that what was being produced in there, the so-called cathode rays, were actually an independent phenomenon. And just to show you how cool and nasty this is, You gotta love a high voltage. So this is about as close to a lightsaber as I'm ever going to get. All right, you too can electrocute yourself for profit and enjoyment using a cathode ray tube. All right, so we have the establishment of the first subatomic particle, but this isn't really known until about 5 to 10 years later. But in 1904, based on what right around this time became the established atomic theory of matter, and having discovered this carrier of negative electric charge, and knowing that elements are neutral by default, so they carry no net electric charge, Thomson proposes something which we now call the plum pudding model of the atom. And it's called this because of this dessert. So this is actually British plum pudding. Okay, it's not what we think of as pudding in the United States. A pudding is more like a cake, and you see it's got like raisins or fruit embedded in the breading. All right, and so that's the idea here, is you have this negative charge embedded in this uniform distribution of positive charge, much like plum pudding. This was the working model of the atom, absent any other experimental evidence, for a few years. It nicely incorporated the electron into the atomic hypothesis, and it was in 1905 that in one of his big papers that year, Albert Einstein really sealed the deal for the atomic theory of matter by describing Brownian motion, which is the jittering of particles inside of gases and liquids without any apparent external force exerted on them. That could be explained by hot atoms. So basically atoms moving very quickly inside the material, bombarding randomly the particles in the material and jittering them around. So random thermal motion due to collisions with molecules or atoms in a substance. Other competing ideas for the nature of elements and compounds couldn't explain Brownian motion. And so that's where you sift the atomic theory of matter out as the leading hypothesis for a description of nature. Okay, well, if you have atoms and they look like this, you should be able to probe this distribution of charge. And that's exactly what Ernest Rutherford did using a series of scattering experiments using beta radiation, fast electrons, and alpha radiation, helium nuclei. So those are +2 positive charge in terms of fundamental charge. Those scattering experiments revealed large scattering angles of the alpha particles back off the target material, which were thin metal foils like gold. This was akin to, as he said it, if the plum pudding model of the atom describes the atom as tissue paper, this is like firing a chemical shell at a big thing of tissue paper and having the shell bounce straight back at your experiment. It makes no sense in lieu of the hypothesis that the atom is a uniform distribution of charge. So he revised the model of the atom to still incorporate the electrons, but pack all the positive charge in a central nucleus. That would explain why you could get large scattering angles for the incoming alpha particles. And so this is known as the Rutherford model, or the planetary model of the atom. You have a central, sort of a star in the planetary analogy. That's the nucleus full of its positive charge, and orbiting electrons. And in Rutherford's picture, those electrons could inhabit any orbits that they wanted. They're simply held in place by the Coulomb force. But there are a couple of problems with this picture. One is that single electrons executing rotational motion around a central potential will irradiate. And so the atom should be fundamentally unstable. This doesn't really work. There was another problem too, and that was that there was a bit of experimental evidence that this model could better explain if it were revised. Niels Bohr, just 2 years later, modified the Rutherford model of the atom to fix the electrons into only specific allowed orbits. Thus, we have the first quantization of the atom. That is, that the energy associated with orbital radii comes in fixed units, and you can only execute transitions between allowed orbital radii. So absent enough energy, you can't promote an electron to the next larger radius with the next larger energy level. And if you make a transition down from a higher energy level to a lower energy level, you'll emit a photon, a particle of light, whose energy is exactly determined by the spacing of the energy levels. So all of this was really necessary because Bohr was interested in using the model of the atom to understand why it was that atomic spectra came in discrete units. That is, they're not continuous if you look at them through a diffraction grating. If you put a high voltage through neon or something like that, or argon, or other materials, and you look through a diffraction grating, there are places where light is and where it is not in angular spread out of the diffraction grating. And so atoms are only capable of producing well-defined frequencies and therefore well-defined energies of photons. This picture nicely explained that observation. So it was a simple modification of the Rutherford model to give these fixed orbits. But there were other problems that were left to be solved later. One of these is something called the Zeeman effect, or the anomalous Zeeman effect. And this was actually something that was observed in 1897, the same year that the electron was discovered. 1897 was actually a really important year for experimental observation in physics. Here's Peter Zeeman over here. This is a photo of him circa 1920. What he observed was, when working with alkali metals, if you subjected the alkali metals to a high magnetic field gradient and looked at the spectra before you apply the magnetic field gradient and after, you see a multiplying structure of the spectral lines. So you go from a single line to a double of lines, or a triple of lines, so doublets and triplets. And nobody could explain this. In fact, the Bohr model of the atom failed to explain this as well, which is why this was an area of active theoretical work even after the Bohr model of the atom was basically shown to be a more successful description of nature. Zeeman observed the effect in alkali metals in 1897, but I actually like this photo you can find off the Wikipedia page on this. So this is actually a spectral line basically from the sun, and so you have a photograph here of the sun's surface. This is a sunspot. A sunspot is a region of high magnetic field activity, so strong magnetic field gradient in this location. If you then observe the spectral line through a diffraction grating, what you'll notice in the region of the sunspot, which is this region right here, is that the lines split. All right, so outside the magnetic field gradient, it's a single line. Inside the magnetic field gradient, you have a splitting. So this is an astrophysics application of the Zeeman effect. This cried for an explanation, which the Bohr model could not give. Well, Arnold Sommerfeld in 1919 attempted to propose a modification of the Bohr model that did explain this. And he argued that what you could do is, for every circular orbit you see in the Bohr model, you could add essentially an infinite number of elliptical orbits with the same energy. So they're degenerate in energy. They all possess the same energy, but they stretch along an axis that you choose. So we could imagine that this is a circle stretching along a z-axis, which is horizontal. Okay, that's typically convention, is to choose the z-axis as the axis of additional quantization. But only, again, certain elliptical shapes were allowed. And so you have here a quantization of angular momentum, orbital angular momentum, along a specific direction, not just out in radius, but also along an axis as well. So an additional quantum number needed to describe atoms. And this is known as the Bohr-Sommerfeld model of the atom. It predicted the existence of space quantization of the orbits, and it was hoped that this would explain the Zeeman effect, but it failed to. So an experiment, a very famous experiment, was done to assess whether or not you could actually observe space quantization, whether this prediction was accurate or not. This is what we call now the Stern-Gerlach experiment, and the idea was that experimenting on beams of sodium atoms, Stern and Gerlach put the beams through a strong magnetic field gradient, so a non-uniform magnetic field. And classically, you'd expect the beam to simply strike the screen and remain in whatever shape it came out in. So let's say circular. If you run it through some circular collimators, you'd expect the beam over here to be circular. But if orbital angular momentum space quantization is present, you would expect, based on calculations of the magnetic moments of the atom and how that would respond in relation to the orbital angular momentum, you'd expect the beam to split. Now, this splitting was very hard to observe, and there's a very nice article in Physics Today from last year, I think, that talks about how a bad cigar led to the discovery of the what we now call the Stern-Gerlach experimental effect. And that was because the original plates they were working with, they weren't doing photographic development. And the beams were so low in yield, and they were getting so little data, you had to do the measurement very fast, that they didn't have time to observe by eye the splitting effect. Thankfully, one of them was a really poor assistant professor, and he could only afford cheap cigars. And he recalled that he had very sulfurous breath from smoking his cigar, and he breathed on the plate, and the reaction between the sulfurous breath and the silver deposited on the surface of the material developed the silver. And it revealed the splitting. Okay, now it doesn't quite work that way. You actually have to inhale the cigar smoke and blow actively cigar smoke. Sulfurous breath by itself won't do it. There's been a modern reenactment of this claim, and it's true if you blow cigar smoke straight onto the plate. Okay, so, you have to be, I guess the story here is that, try anything. You never know. You never know when discovery is going to happen. You just kind of have to be open to the possibilities. Don't be afraid to try something that doesn't make sense at the time. Okay. So, in fact, they saw the splitting, even though it was very tiny. They were able to verify that space quantization is real, but its implications were not fully realized until about 5 years later. What they didn't know at the time is that the silver atoms were in their ground state, and so they had no orbital angular momentum in this beam, and yet the beam split anyway. And the reason it split is because electrons carry a little unit of internal angular momentum, which we now call spin. Originally, it was believed that the electron itself was spinning, but you'll have some homework on that to assess the reasonableness of that kind of classical model of electron spin. Okay, that turns out not to be an accurate picture of what's going on. What's really going on is that particles like electrons simply carry as an internal quantum number an indivisible unit of angular momentum. It's what identifies them as a certain class of particle. Fermions carry half-integer spin, bosons carry integer spin. And they have different statistics that apply to them as a result in bulk materials made from those kinds of atoms, different kinds of materials. Okay, so you have here, this very rapid period of development of about 25 years or so, where you have ad hoc model, experiment to test it, revision of the ad hoc model, experiment to test its implications, revision of the ad hoc model. This is really how this progressed. It wasn't lone geniuses working quietly in obscurity in closets and institutions. These were people interacting with one another. They were doing experiments. They were doing calculations. They were trying to understand. And it really demonstrates beautifully the interplay of theory and experiment in developing a more reliable description of nature. So that's why I wanted to go through this, okay? So this is sort of our modern picture now. I use the classical bias here and draw the electron as a sphere, although it's not. As far as we know, it's a point. And we've never actually measured its physical extent to be anything finite. It carries an internal unit of angular momentum, and exposed, for instance, to a magnetic field, you can get the spin to align either with the magnetic field or against the magnetic field. The magnetic field picks out a preferred direction in space, and so we would refer to those as two different spin states, spin up and spin down, and we'll come back to that in a bit. But the electron, again, is not actually spinning. Uhlenbeck was the one who sort of tried to work that model and found out very rapidly that it fails. Okay. All right, so I'm going to turn the lights on, so you're all going to have a seizure. All right, there we go. Okay, so that's the basic brief introduction as to the history of spin as an idea. What we're going to do now is switch gears completely and go into kind of a review of the mathematics that you're going to need to pick your way through this material. Some of this, probably a lot of this, is going to already look familiar, but I go through it because, much like warming up before a half marathon, it's important to do some exercises to train a little bit, and so this is training, all right? So, with that in mind, let's start with the most basic things we're going to need, and that's complex numbers. So these are represented as usually by the symbol z. This is a little z. This is how I draw my z's, okay, so that they don't look like my 2's, which is a real problem that I have. Now, a complex number can be made of two pieces, a real part and I times an imaginary part. Now, both of these are real numbers. This is a real number. This is a real number. What makes this the complex piece is it's multiplied by I. All right, so your goal is to makes it an imaginary number is that it's multiplied by I. So your goal with the imaginary piece is always to pull the I out in front and then isolate the real number that's left over. And this can be written as a more simplified version, x plus iy, okay? And then very quickly we can define an important concept that comes up over and over and over and over again as we continue to use complex numbers, and that's the idea of the complex conjugate. So the complex conjugate is just swapping the sign of the imaginary side of the complex number, okay? All right, so then from this you can develop a whole question about, well, okay, what is the magnitude of a complex number? We want the magnitude of a complex number to be a real number, okay, a real valued quantity. So if you're interested then in the magnitude, this is written as the square root of z times its complex conjugate. That's, if you check that out, right, you played around with this before, that product will be guaranteed to return to you a real number, okay? And so this just winds up being the square root of the real part of z squared plus the imaginary part of z squared, All right, so there's no magic in any of this. I'm reviewing this just to be very basic. The other thing you can do is you can actually write the real and imaginary parts in terms of z and its complex conjugate. This also becomes very handy. For instance, later on when you're playing around with the Schwarz inequality and using that to determine the uncertainty principle, okay, which I'll come back to in a bit, the Schwarz inequality is the key to the uncertainty principle in a general sense. And it's very helpful to have some of these relations in mind. All right, so the real part of z, and again, this is something you can play around with algebraically, is the sum of the number and its complex conjugate divided by 2i. And the imaginary part of z is z minus z star. 2 pi. What's that?
It's just 2, not 2i.
Just 2i, yes. Excellent. And then this one is 2i, yes, to get rid of the I. Okay. All right, excellent. So, bonus points. You found my first typo. Just 2. Yeah, it's like a game show on public radio. You get an arbitrary number of points for pointing out, totally subjective, arbitrary, and useless number of points for pointing out mistakes. So, okay. Another thing that's useful is that, and this seems like a trivial statement, but if you are looking at z times z star, the real part of the number z squared will be less than that magnitude, and the imaginary part will be less than that magnitude, okay? Or less than or equal to if there is no real part, okay? So just some simple basic things. Okay. Now, vectors, okay? All right, so once you get to college, you have this, well, even in high school, you usually have this beaten into you. Okay? So a vector is just a multi-dimensional storehouse for real numbers, complex numbers, something like that. All right? So we can have a vector R, which has components x, y, z. All right? Or we can have a four-dimensional vector, which we run into in relativity, where you add a time component, okay, multiplied by the speed of light to give you units of distance, okay? So we're used to thinking of vectors in a very space-time conventional way, but it's important for quantum mechanics to generalize the concept of a vector, okay, and then to develop basically some practice with that. So, okay. So one of the things that will help here to generalize this is something called Dirac notation. All right, so rather than having a symbol with a little vector over it for a three-dimensional vector, Dirac notation has this structure: vertical line, letter, and then a angle bracket. All right. So this is a column vector. So if we were going to write this as R, if we were just going to rewrite that vector R with the little vector symbol as something in Dirac notation and put it in what's called the matrix representation, in this case a column vector, that's what that notation stands for. Now you can imagine that, well, it would be handy also to have row vectors, all right? I'm going to revisit this symbol in a moment because what I'm about to write on the board is not complete, but you might imagine that if you were going to write a row vector, you might just flip this thing around. Okay, so far I'm sticking, for now, real numbers into this thing. You'll see in a moment that when you put more general numbers in there, complex numbers, you can't just do this. Otherwise, you can't preserve things like the definition of length as a real number and so forth. Okay. So, in general, really, a vector can be a structure that contains anything, including complex numbers. So in general, you can define this kind of structure over the field of complex numbers. Okay? And in that case, you want to do things like preserve the definition of length as a real number. So here, if you did r dot r square rooted to get the length, this would be an element of the real numbers. And we want to preserve that definition in the generalization of vectors. So in this notation, in this Dirac notation, what we want is we want this thing to also be an element of the real numbers. That is, to preserve the definition of the length of a vector. To do that, you can't just transpose the column vector and make it a row vector. You also have to take the complex conjugate. All right, so in reality, you have to take the complex conjugate of the elements when you do this. Otherwise, you can't preserve that definition. Okay, now, this is the part that I always hated when I learned this. This is a ket, this is a bra, and this is a bracket. Okay? It's cute and annoying all at the same time. I never liked this notation, and I never liked what it was called. But there we have. We're stuck with it. Dirac's way smarter than any of us, I guess, so we get to stick with his notation. Okay, so that's very general. And then if we wanted to write this in terms of, you can write bras in terms of kets and vice versa. So in this case, R is just equal to the transpose complex conjugate of the ket, R. And this has a special notation, dagger, which means adjoint. All right, so the transpose complex conjugate is the adjoint. Okay, so just a lot of basic terms you probably all heard before. Okay, any questions here? All right, yeah, I didn't think so. Or at least I hoped not, so. All right, so.
I have a question.
Yeah.
When we write a four-dimensional vector, do
Yeah.
you put time
Yeah.
first or last?
It's up to you, as long as you handle the rules of four vectors where you're attempting to calculate the space-time invariant. So something has to get a minus sign in the square. So either it's time or it's all of the space components. It depends on the so-called metric that you choose, right? Yeah. So the other thing you can do too is, I think this was convention a long time ago. It's much less convention now. Would be that you can, for the four vectors, you can put I in front of this. So you can write this component as ICT. Then you square the components and add them, but this one gets an automatic minus sign. That was an older way of doing it. I prefer the metric language, where you just decide that, look, I need to preserve something about my structure in space-time. I need invariance, and so this is the metric that will achieve that. So, yeah, it's, conventions change.
So
Yeah.
particle physicists, they do all space negative, and then GR is the time.
Yeah, that way the rest,
That sounds right, yeah.
that
The-
way the rest mass is positive.
Oh, yeah.
Yeah.
So,
right.
If you did the,
Right.
the GR guys do it the other way, and then negative rest
if you have-
Okay, so, basic notation, now, vector spaces. All right, so a vector space is simply defined according to a number of properties. We can denote this as double line V here, okay? So, there is a definite rule for addition. Okay, so for instance, there's some operation that lets you sum the two vectors. And we'll come back to what the sort of end point of that property has to be. There's also a definite rule for scalar multiplication. Okay? So in other words, if you have a bunch of scalars, A, B, dot, 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 okay, then you can define some kind of product, A times a vector V. Now, the key here for these two things is the following. First of all, these operations result in another vector in V, in the space. Okay? So if you add two vectors V and W, you get another vector Z, for instance, that's in the space. All right, so here, this has to be an element of V. And multiply your vector by a scalar, this too must be an element of V. Those are the requirements for those two operations. So basically the space is closed. You can't make a vector outside the space by doing these operations. That's the requirement for a vector space. So if you are given a set of vectors and asked, is the set closed, based on some definition of multiplication and addition, you can then test to see if you ever get a vector outside the set you were originally given. If that's the case, it's not closed, and therefore it's not a vector space. Okay, more basic stuff. And I like the way that Shankar puts this. Basically, when it comes to vector spaces, if you're having a hard time remembering what to do what comes naturally, which is a good way of remembering it. Okay, so we have the scalar multiplication is distributive. All right, so in other words, if you have a plus b times a vector, a ket v, this is a ket v plus b ket v. Okay, and again, that will give you another vector in the same space. So that's one thing. Another thing is that the scalar multiplication is associative. All right, so in this case, if you have a scalar A times B times ket V, right, so that's already been grouped together as an operation, it's the same as AB first multiplied by one another, then multiplied by ket V. Okay, so that's association. You can just reassociate which things happen first and it doesn't change the answer. Addition of vectors is commutative, commutative, one of the two. Commutative. Okay, so very simply, if I have ket V and ket W added together, this will be the same as if I swap the order of addition. Okay, nothing changes. You get the same vector Z, let's say, from that addition. Surprise, surprise. Addition is associative. Okay, so in this case, if I have first ket V and ket W added together, and then add that to ket Z, that is the same as V added to first summing ket W and ket Z. Okay, so associative. Nearly there. This is the boring stuff, right? Okay. Again, do what comes naturally. And these are things you probably would have already done so many times with vectors of the space or space-time format that you don't even know that you're doing it anymore. Okay, there's a null vector such that if you take ket V and add it to the null vector, which I'll denote as ket 0, you get back ket V. It does nothing under addition to the vector. And then for every vector, basically every vector has an inverse under addition. And basically what that means is that if you take V and you add its inverse vector to it under addition, which I'll denote negative ket V or ket negative V, you get the null vector back. So they cancel each other out and you have the null vector. Now, the scalars, so that's sort of the end of the properties of the vector space. The scalars,
What about the identity?
I think the identity can be derived from this. The existence of the identity operator, if I remember correctly, is a consequence of these postulates.
Oh, okay.
Yeah, I have to check that for sure, but that's why I didn't include it here, because I thought that was if you wanted to go prove it, I think you could prove it exists.
I think all this is properties of a group. Isn't that?
Yeah. Well, groups are slightly bigger than this. I think there's one more thing that they require, but yeah, At some point, you realize, oh, this is just a subset of a group under these conditions, and therefore it'll behave this way. And yeah, you can go really deep on this if you want. So
Because I think if you get like all but one property in a group, you can use the other remaining ones to get the last property.
Yeah.
So I think that might be.
yeah, yeah. It's been a long time since I did formal group theory, but I remember playing games like that. So, and not being very good at them, I might add. All right, so the scalars involved are known as the field over which the vector space is defined. Okay, so if the A's and B's over here are complex numbers, then the vector space is defined over the field of complex numbers. Okay, now the other thing that's going to be the case, because this is all we really need for quantum mechanics, is we're only going to deal with linear vector spaces. Okay, so these are spaces where ket W can be written as a sum I equals 1 to n of scalars times ket V's in the space. All right, so basically any vector can be written as a linear sum of other vectors in the space. And that's the only kind of space we're going to deal with. That's all we really need. Okay, a few more things here. All right, linear independence. And basis vectors. All right, so we can define an important feature of a subset of some vectors in the space V. All right, so there can be vectors that when they are, let's see, here we go, when they are multiplied by scalars and summed, yield the null vector. Okay, so it's possible that such a combination could exist. And should such a combination exist, this set, so the VI, the ket VIs, are linearly independent if you have more than just the trivial case that the scalars are all 0. Okay, so if some of the AI are not equal to 0, at least one or two of them, okay? You're going to need 2, at least 2. All right, so basically they're linearly independent if there's no combination of multiplicative scalars that leads to a null sum. Oh, sorry. Let me take that back. Linearly independent, had that backward, only if AI equals 0 achieves this condition. My bad. Knew something didn't feel right about that. Okay. So you have a set of vectors and can think of it in 2 dimensions, right? So if you have vectors that lie nearly parallel but not exactly parallel to one another, you can actually arrange it so that they can cancel each other out. But if you have vectors that are at right angles to one another in a 2-dimensional space, the only way to get them to cancel out because they have no components in common is to multiply them both by 0 and add them. That's the only way to get the null vector. So in a space sense, orthogonal or vectors at right angles to one another are the only ones that can be basis vectors in a coordinate system, right? Or linearly independent. And a set of linearly independent vectors is called a basis set. Right, if it spans the space. And what's the definition of spans the space? What does that mean?
It means that, how do you say it?
Any
It's
vector can be comprised.
Vectors in the basis,
Yeah, vectors in the base. So any vector in the set, and any vector in the space can be written as a sum of those basis vectors. And you don't need any more vectors to accomplish the sum than those. I mean, that's maybe a working definition. But humor me, I'm an experimentalist, right? So conceptually, conceptually you know what this means. It means if it's possible, if I have a basis set of two vectors in a three-dimensional space, I know that it's possible to write some of the vectors in terms of the sum of those two and another. So that's not a complete basis. I need three basis vectors in a three-dimensional space to be able to define any vector in the space using a linear combination of the basis vectors. All right, so that's maybe a working definition. It can be generalized, I'm sure, much more fundamentally and mathematically, but that's the working definition.
You need a square matrix.
Yeah. If you think about an n by n matrix, an n by n matrix is an operator in an n-dimensional space, and so you have to have a set of basis vectors capable of basically giving you all of the columns uniquely in that 3 by 3 matrix. Right. We'll come back to that in a bit, actually. So, okay, another thing that you need is, and we already sort of touched on this a little bit earlier, but I'll just come back to it one more time and do the jargon. We need a scalar or inner product. And you'll see why it's called an inner product if it isn't already something you've seen before. Basically, in space vectors, if we think of vector A and B in a two-dimensional space, the scalar product A dot B is equal to the magnitude of A, the magnitude of B, and the cosine of the angle between them, theta. So here's theta. Okay? So that's a space vector case. We want to generalize this. Basically what we're saying is we're calculating the projection of either A on B or B on A. Okay? So it's the component of A that lies along B. That's what you're calculating. We want to do that in general for our Dirac notation, so general vector spaces. So we want to define a product, bra W, ket V. So there's one of our brackets, okay? And in our case, this can be an element of the complex numbers, okay? All right, so this is the inner product.
Doesn't that have to be
It's
real?
real.
Sorry, yes, real. Yeah, because the length, if you do V with V, you always get a real number. So W with V should also only be a real number. Yeah. Okay, and so, so then this lets us generalize the definition of length. So the length squared is just equal to bra V ket V. And then we can take the square root of both sides to get the actual length of V. Okay, let's see. I think I'll skip over the next few things. They're just properties they're axioms that are demanded to be obeyed by the inner product. Skew symmetry, positive semi-definiteness. One thing, actually that's worth saying here. So it's required in our vector space that this be greater than or equal to 0. This is referred to as positive semi-definiteness, and it's actually a very handy property to enforce on your vector space. Later on when we talk about the uncertainty principle, you'll see why. Okay? It's only exactly 0 if this is the null vector. So if V is ket 0, if ket V is ket 0, then you get exactly 0. Okay, a couple of other useful things.
Good question.
Yeah,
Aren't the reals a subset of the complex numbers anyway?
they are, yeah.
So even with the C there, it's true.
Yeah, in fact, let me think about this a second. It's possible.
Just a special case for all the imaginary. Well, the imaginary side is 0.
Right. Okay, no, so it is actually generally true then that this can be an element of the complex numbers. In fact, for skew symmetry, that's why bra V ket W is equal to ket V bra W complex conjugate. Okay, so it's not guaranteed that that's only an element. That is guaranteed to be an element of the real numbers, but that's not. Yeah. Always, in general? But then why would skew symmetry have to be enforced as an axiom in that case? Because then it would be guaranteed that, that the inner product would be equal to itself if you reversed both. No, you're right, it does have to be real. Skew symmetry just enforces that when you swap these two, it comes at the penalty of a complex conjugate. So skew symmetry just requires that this be equal to this. It's still real, but the only way to actually get those things to be equal is to take the complex conjugate of the vectors when you swap their order. Which goes back to what I said earlier about bras are the transposed complex conjugates of the kets. So they're a space that's dual to the ket space. Okay, yeah, some more properties here, and then we're almost ready for the first exercise. We'll break up the monotony of this a little bit. I knew this was going to be boilerplate, so I appreciate you toughing it out. Okay, so orthogonality. If the inner product of two vectors is 0, so two different vectors, W and V get an inner product of 0, then it is said that they are orthogonal to one another. So again, you can conceptualize this in a two-dimensional space. The inner product of a unit vector along the x direction and a unit vector along the y direction vanishes. They're at right angles to one another. So this is where this comes from. Let's see, so the norm. The length of a vector is referred to as the norm. Okay, or the length. Of ket V. And then finally an orthonormal basis. This is a set of basis vectors, all orthogonal and unit length. Okay, so if you have a set of basis vectors, the way you get them to be unit length, let's say you've got VI, okay, but they're not necessarily unit length. You can convert them to unit length by taking the vector and dividing by the magnitude, the norm of the vector. If it's already unit length, then the denominator will be 1, and it's a trivial division. If it's not, then you'll get in the end a unit vector whose length is 1, and maintain the orthogonality of the basis vector set. Okay, so that's going to come in handy for the next step. Okay, so last two pieces, and then we can do some exercises. Once you have a set of orthonormal basis vectors, you want to then express other vectors in the space in terms of those. Okay? So it should be possible to take any generic vector V in the space and express it as a sum on, let's say, I of coefficients VI times these orthonormal basis vectors. Okay, so these kets I. If you wanted to find the jth component, okay, jth component of ket V, you'd simply take the inner product of the orthonormal basis vector J with V. All right, so this just gives you the sum on I. Vi is a number, Ji. Now, because these are orthonormal vectors, the only time that inner product won't vanish is when I is equal to J. Oops. So we pick out Vj, j, j. And this is just 1, since these were defined to be orthonormal basis vectors in the first place. Okay, so this seems like a fairly trivial solution, but what you learn is that the jth component of the vector v is just given by a number, which is the coefficient for that particular component in the sum, vj. And in using this result, you can then expand any vector in the space into the sum of orthonormal basis vectors. So I equals 1 to n, ket I, bra I, inner product with ket v. So this is vi, this is the little scalar vi right here, the ith component of the vector v. This is a handy notation because if you use this in a situation where you have to expand a vector out into its basis states, you can then very quickly determine what parts of the product disappear and what parts of the product remain. Okay. All right, and then finally, let's say you want to find an orthonormal basis set. This is the application of the so-called Gram-Schmidt theorem or the Gram-Schmidt procedure. All right, and it's just an exercise in calculate, rinse, and repeat. Okay. So let's say we have a set of vectors Roman numeral 1, Roman numeral 2, Roman numeral 3, etc., that span the space and are basis vectors. Now, they're not necessarily orthogonal to one another, and they're not necessarily unit length. And you want to get a set of orthonormal basis vectors from this set of basis vectors. The way you do this is you apply the Gram-Schmidt procedure. Okay, so step 1. Start with one of the vectors. Okay, so this is suggestingly numbered 1, so we might as well start with that. We want to get a ket number 1, okay, Arabic numeral 1, whose length is 1, and that's all we want for the first one. We just want a vector whose length is 1 to start with. And to get that, we can just do what I showed you before. We can take I, and we can divide it by its length. And this, by construction, this is unit length by construction. Okay? That's the easy step. The second step is slightly harder. You now need to take another vector in the space and orthogonalize it with respect to Arabic number 1. So ket Arabic number 1. So let's call this, for now, ket 2 prime. Okay, because we're going to orthogonalize it, but no guarantee that it has unit length. We'll get to that in a second. All we have to do is take Roman numeral 2 ket and subtract off the piece that projects along the direction of Arabic numeral 1 ket. Okay, so to do that, all we need to do is subtract off that piece. All right, so that's just the magnitude of the projection of 2 along 1, and you're subtracting it off. Okay, so that's the direction, and that's the magnitude of the projection, and then you subtract it off, and now you can go ahead and play around with this. If you multiply 2 prime by 1, you'll see that you wind up getting a 0, null vector result out of that. So by construction, this is orthogonal, but it's not normal. To get it to be guaranteed to have unit length, you need to take 2 prime and divide it by the magnitude of 2 prime. Okay, and you can see where this is going, right? You keep going. And so this just becomes an exercise in algebra until you can't stand it anymore. The third step, to get 3 prime, you take Roman numeral 3, subtract off the projection along the first orthonormal unit vector, and subtract off the projection along the second orthonormal unit vector. That's guaranteed to be orthogonal to the first 2 that you found, etc. Okay? Similarly, okay? And keep going. So hopefully you never have to deal with more than a 3 or 4 dimensional space. All right? So in the spirit of getting some practice with vectors, let's do one. So everyone have scratch paper or can borrow scratch paper from somebody else? So let's take, I don't know, about 10 minutes or so and just do these. These should be fairly straightforward. All right, so you've got a couple of vectors here, Roman numeral 1 and 2, and they're given in the column, the matrix column format, column vector format. First thing is just compute the complex conjugate transposes of the vectors. That is the bras that correspond to these kets. Okay, so you're going to get the adjoint of the vectors. Calculate the length of each of the vectors. Demonstrate that the vectors are not parallel to one another. And then use the Gram-Schmidt theorem and create from these vectors an orthonormal basis vector set. All right? If these are in the notes, so if you're having a hard time reading on the screen,
let's roll on.
let me
I don't
know
want
and I
you
can
guys
hand you
to
the
sleep
notes.
too quickly today.
So my notes were a little out of order. It would have been nice if I had done the Schwartz inequality before giving you number 3 on the in-class representation. But basically, to demonstrate the vectors are non-parallel, you want to know, first of all, if you were to demonstrate that their product were 0, you'd automatically know that they were non-parallel because they'd be orthogonal to one another. But if they're not orthogonal, then you kind of have a range of possibilities, and for that it helps to know the Schwartz inequality. So the Schwartz inequality just is a statement about the length of the inner, so the magnitude of the inner product of two vectors, v and w, with the product of their individual magnitudes, mag v and mag w. And the Schwartz inequality, which you can go ahead and prove it if you want, you need to use the positive semi-definiteness feature of all the vectors we're talking about here. But if you take that axiom and employ it, you can show this relationship is true. If you find out that, in fact, this left side is not equal to this right side, then you know that they're non-parallel. Okay, so you kind of need 2 things. Certainly if they're orthogonal, though, you know they're immediately not parallel. Okay, changing topics a little bit, we now want to concern ourselves with operators and specifically linear operators. So an operator is any object A that when it multiplies ket V returns another vector in the vector space, so ket W, let's say. Analogously, in physics, operators are, if the kets represent possible states that a system can be in, the operators are the measurements acting on those systems to measure their properties. So that's the language we'll adopt once we get into the Schrodinger wave equation and then angular momentum. But quite simply, if you're in a generic vector space like the one we're talking about, an operator is an object that acts on a vector and returns another vector in the space. All right? This is also possible. The operator can act on the dual space, the bras instead of the kets, and return another bra. I actually have that backward in my notes to fix that. Fix. Okay, now we're specifically concerned with linear operators. You can already imagine if you start writing your vectors in the matrix representation. So here's a unit vector v, for instance, in a 2-dimensional space. The operators are going to be matrices that are 2 by 2, acting on this, which will return another vector in the space. Okay. So in the matrix representation, these will be n by n matrices in an n-dimensional space. Okay, so we're interested in linear operators. So linear. What does that mean? Basically, it means 4 things are satisfied. So basically, that means 4 things are satisfied, 4 rules. If you have an operator acting on a scalar times a vector, you can simply swap the order of the scalar and the operator at no penalty. Okay? You can distribute the action of an operator on 2 vectors. So this just becomes alpha A ket V plus beta A ket W. That's another requirement of being linear. And then exactly the same rules, but applied for bras instead of kets. Okay, so for instance, if you have bra V A, or alpha times an operator, so again, here's a scalar, here's an operator, then this is just equal to bra V A alpha. Okay, and then similarly, you can repeat this rule for the bras down here. Now, the simplest operator is the identity. Which comes in immensely handy when we start talking about eigenvalues. So we can represent this by the capital letter I acting on a state V, a ket V, simply returns the ket back to you unchanged. Okay, so that's the identity operator, and it satisfies this behavior for all bras and all kets in the vector spaces. Okay, lots of properties. I can only survey some of the properties of matrices. So I kind of cherry-picked my way through the ones I felt were going to come in the most handy. First of all, unitarity. All right, so if you can take the complex conjugate transpose of the operator, so if you think of a matrix, you swap everything around the main diagonal and take the complex conjugates of all the elements, and you multiply that by the original operator A. This is equivalent to that dagger operation, the adjoint operation that I mentioned before, times A. This returns to you the identity matrix. Okay? So that's one useful property of a matrix. If you can determine that, it can greatly simplify calculations. All right, so a matrix is Hermitian if A dagger equals A. That is, if you do the adjoint operation, you get back the same matrix that you started with, then it's a Hermitian matrix. Determinants. I'm going to let you go and look up the general form for calculating a determinant, but we can do the simple case, two simple cases, okay? So the determinant is a number that represents the matrix. And it's calculated, so let's say we want det of A, which is equal to the determinant of A, B, C, and D. So let's say it's a 2 by 2 matrix. That's what A is. In this case, it's a number, and the number is equal to AD minus BC. BC. There we go. If you have a 3 by 3 matrix, I'm going to pull in this here. So let's say you have the determinant of a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. This is going to be equal to A, eliminate the column and row that A are in, and calculate the determinant of the remaining 2 by 2 matrix. So it's going to be EI minus FH. Plus B, do the same thing, eliminate column and row, DI minus FG. And finally C times eliminate column and row. It's going to be DH minus EG. Okay?
Need a negative sign on the B.
Need a negative sign on the yes. Thank you. Okay. Good. That explains a sign error I was having in my solutions.
Sweet.
Excellent. Okay, thank you, Ben. Yeah. I was going to track that down later today. Okay, so that's just some handy things. You can look up in a textbook or on Wikipedia or Wolfram Alpha, Math World, whatever it's called. You can look up determinants for arbitrary matrices. We won't go past 3 by 3. Okay, so these are already the ones that will come in handy for you. The reason I bring this up is that the determinant of a matrix that's Hermitian, okay, that's its own self-adjoint, is an element of the real numbers. Okay. All right, so there's a bunch of other stuff. I'm gonna let you look at the notes. There's no sense in going through these one at a time. The ones we really need, the stuff we really need is coming up next anyway in the next section of the notes. But there are a few more in the notes that will come in handy for solving problems. Okay. Elements of a linear operator. So it's helpful to be able to figure out from the action of the operators on vectors in the space, what the individual elements of the n by n, let's say, operator matrix is in an n-dimensional space. Okay, so we'll kind of go through this in the same way that we went through writing down the representation of an arbitrary vector v in terms of basis, orthonormal basis vectors in a space. All right, so I'll start over here. Okay, so the action of an operator, what it does to vectors in the space, can be entirely specified by its actions on basis vectors. Why? Because any other vector in the space can be written as a sum of the basis vectors. So if you know what the operator does to the basis vectors, you can instantly calculate what it does to any other vector in the space. All right, so let's say we have a set of basis vectors I, and we have some formula that tells us what the operator does to those basis vectors I. It transforms them into I prime, for instance. In that case, we can then write the action of this operator on any vector in the space. So if we have A times vector V, that's going to be A times the sum on, let's see, I chose I for this one, which is probably foolish in hindsight. Of, I is fine. VI times the basis vectors I. Actually, that works out okay. All right, so again, we're just writing the vector v in terms of a sum of the basis vectors multiplied by scalars, whatever sum is needed to achieve the vector v. We can move the operator inside the sum and swap it with the scalar multiplying this, because these are linear operators. We're allowed to do this. So we have vi, a, I ket. Okay, and we know from this formula what it does to basis vectors. So we have vi, I prime. Okay, so now we can then say, well, what happens if we then take the inner product of this formula with another basis vector j to get components of this new vector over here? All right, so we can take j, we can take the inner product of that with I prime, and that's just going to be equal to j, a, I, and we define that to be the ijth element of the operator A. All right, so this activity here, this operation, picks out a specific number inside of the operator and isolates it. All right, so in the matrix representation, that would be the I comma j element of the operator, the matrix elements. And then we can write the components of that vector v, again, in a suggestive way that will help us to, for instance, determine the form of operators whose actions are known on the basis vectors, but whose elements are not actually known in advance. That's why this is useful. Okay, so the component of a vector vi, let's say we have, let's see we have a vector v prime whose components are these coefficients vi prime. So these are just going to be equal to, let's see, the ith basis vector times v prime, so bra I ket v prime. That just picks out the ith, the projection of v prime along the ith basis vector, which is this coefficient. Okay? And this is just going to be equal to I a times some other v in the space. And we already were able to expand that in terms of coefficients. So that's going to be I a times the sum of j equals 1 to n, vj ket j. All right, and we will put this in parentheses here. And so we can finally move some things around. We can move the operator inside the sum, swap with the scalar that's multiplying the basis vector. So we'll do that all in one step. And we wind up with, let me start with the sum here. J equals 1 to n. I, v, j, I, a, j. Okay, which this is just the I comma j component of the operator. So we just wind up with the sum j equals 1 to n, vj, aij. So the product of two numbers summed up. Okay, this doesn't look all that useful, but it helps to schematically write this out. So imagine you have an arbitrary n by n matrix. Okay. So the reason this is helpful is imagine you have an arbitrary n by n matrix that transforms v into v prime. So the components of v prime can be written in the matrix representation as little v1 prime, little v2 prime, all the way to vn prime. And we know that that's the result of an operator n by n in size acting on the original ket v, which we can write as v1, v2, all the way to vn. And again, remember, we're given the action that the operator has on a basis vector. All right, so we know what it does to transform basis vectors. So all we have to do then is take advantage of that information and write down the matrix elements using that formula which I've now covered out, which is right here. Okay, so that you can determine the aijth component by this product of the ith basis vector times a times the jth basis vector. So up here we're in the 1, 1 position, I comma j 1, 1. Over here we're in the 1, 2 position, okay, etc., all the way up to 1, a, n. Here we're in the 2, a, 1 position, all the way down to n, a, 1. And then finally, all the way down in this lower right corner, we have the nth basis vector, a nth basis vector. All right, so let's exercise this. Another exercise. Let's put this to use. Okay, so let's define a rotation operator. Its action on the basis vectors in a three-dimensional space, and I'll show a picture in a minute, is to rotate basis vectors by 90 degrees around the x-axis. All right, so here's my right-handed coordinate system, x, y, z. All right, so its job is to rotate basis vectors around x. And it does it by 90 degrees. So it does it like this, okay? So when it rotates by 90 degrees, it changes, let me see here. Yeah, it changes the z-axis, changes the y-axis into the z-axis. So actually it's x, y, z. Sorry about that. X, y, z. So it changes the y-axis into the z-axis, and it changes the z-axis into the negative y-axis. All right, and that's easiest to see if I skip to the next page here. There we go. Okay, so if you rotate counterclockwise around x by 90 degrees, y becomes z, and z comes over here and becomes negative y. Okay, x is left unchanged. All right, so that's all those formulas tell you. This operator, r 1/2 pi I vector, it's just a notation. I is not a complex number here. It's just I vector, the direction I. All right, acting on the basis, orthonormal basis vector I, it leaves it untouched. So it's like the identity operation for that axis. But for j and k, it changes j into k and k into negative j. What I want you to do is figure out what are the matrix elements of that rotation matrix using this trick. All right, so all we know is what it does to the basis vectors, but this is very powerful information because once you know it, you can write down generally whatever the form of that operator is in the matrix representation. And we could do this for arbitrary rotations. This happens to be easier, but we could do it for arbitrary rotations through angles theta or theta and phi if we want to do all three dimensions.
I wish they had a, so I don't know where, I can
Yeah,
decide
yeah,
is.
I'll see what it is.
Okay, let's go ahead and get started so we can all be free for today.
Yeah, you don't know.
All right, I'm going to erase.
I've never met the shop.
Yeah, no one has.
Maybe
I don't know what he looks like, so I've never met him here.
Okay, commutation. This is something that's really essential to feel comfortable with in this operator business. Commutation is concerned with the question of whether the act of A then B operating on a vector V is the same or not as B then A acting on the same vector V. All right. If that's an equality, then it's what is said is that the operators commute. If that's not true, then they don't commute. Okay? So we can consider these rotation operators. So we have one set already. These operators rotate by 90 degrees around the x-axis. But we can consider another set that rotate by 90 degrees around the y-axis, so around the j vector direction. All right. So what do? I'm going to denote this just for simplicity as rj. Okay, just so I don't have to keep writing 1/2 pi all the time. Rj, acting on the x-axis unit vector, gives you negative k. All right. So if we rotate counterclockwise around y, x rotates down here and becomes negative z, so negative k. Rj acting on the j vector trivially just leaves it alone, and Rj acting on the k vector yields the I vector. Okay? So that's the action of these operators, and then we can ask what seems like a fairly simple question. Does it matter if I rotate around x then y, or first y then x? Does it make a difference? And you can already gather that there's an answer to this, which is not trivial. Okay? So if we have Rj, Ri, those are the Ri up there, acting on j, this is just going to be equal to Rj acting on k, okay, because Ri acting on j gives you k. So now we have Rj acting on k, and that gives you I. We can swap the order. We can say Ri, Rj, acting on j. Okay, so in this case, we have Ri acting on j, because Rj acting on j leaves it alone. And then finally, we then rotate j around the I direction, and we get k. Okay, and so we can see here's a specific case where, in fact, the action of the operators does not commute. It's not true that Ri, Rj is equal to Rj, Ri. Okay, so one way to notate this is this bracket notation. Okay, this is the commutator. And you're usually concerned with the question of whether or not this is equal to 0 or not. So this is just equal to Ri, Rj minus Rj, Ri. If those two things are equal, that's equal to 0. If they're not, then it's non-zero. Okay, and you'll see why this is really fundamentally important for operators in a moment. But that's the gist. All right. So it is not true that all operators will commute with one another. When they do, something very special is going on, but in order to understand that, we have to go through eigenvalues and eigenvectors first. Okay, so any questions there? Okay, let's talk about eigenvalues and eigenvectors. Eigenstuff. When I first learned about eigenvectors and eigenvalues, it was referred to as the eigenvalue problem. And at the time, I wasn't such a bright student. And so I remember asking my tutor, why is it a problem? And he's like, no, it's just something you solve. It's actually a good thing, right? Which no one had bothered to make clear to me, all right? But once he said that, it was immediately obvious to me why it was so useful, okay? All right, so now we're interested in eigenvalues and eigenvectors. We all have our moments of weakness. Okay? So, in general, an operator's action on a vector is some complex combination of rotations and other things that the operator is doing to the vector to return another vector in the space. But there are a few, as Shankar puts it, privileged vectors, which when acted upon by an operator simply return the vector multiplied by a scalar. All right, so we can imagine an operator A acting on some special vector V, and the action of that operator is merely to return V multiplied by a scalar. So you're just changing its length in the vector space, essentially. We can rewrite this equation in a very suggestive format. This here is really just A times the identity operator acting on V. But by writing it this way, it allows us to pull this over to the left-hand side and have an all-operator equation acting on V, which yields the null vector. And this is the fundamental form of the eigenvalue equation. The eigenvalue and eigenvector problem is entirely concerned with finding the V's and finding the A's that satisfy this equation. Now the next step, where you solve for the eigenvectors, gives you an equation. Its pieces are a bit messy. I'm not going to talk about all of them. I'm only going to talk about the one that really matters, and that's the determinant that's involved in what happens next. You can take a matrix, and you can find a matrix, A minus, which is the inverse of A, okay, such that A minus, A to the minus 1 acting on A yields the identity vector, okay?
So what's the difference between the minus and the A dagger?
A dagger is not just the, well, in that case, for a unitary matrix, the inverse is the adjoint. It is not necessarily true for other matrices that are non-unitary, that the adjoint and the inverse are the same. That's why that's so powerful. Because in order to calculate the inverse of a unitary matrix, all you have to do is transpose its elements and take the complex conjugate. It's greatly simplified. In general, however, the inverse of a matrix is not equal to the adjoint, not necessarily. It's much more painful to calculate. And that's why I'm going to skip one of the details in this, okay? So,
in order
yeah.
to, in quantum mechanics, all of the operators we look at will either be unitary or anti-unitary, right?
I think that's, yeah, that's constrained.
I can't remember why that is. There's only one that's anti-unitary. It's because of the it's because of the hermiticity.
It's the hermiticity that
That's
does
right.
it. Right,
That's right.
Right, exactly, yeah.
There's only one that's anti.
All right, so you can imagine that for this matrix, there presumably is some inverse matrix that when multiplied by this yields the identity matrix. So let's just write it notationally as this. So this equation is just a rewrite of this one. The eigenvectors are simply equal to the inverse of this matrix times the null vector. That's not really a useful thing, because unfortunately the null vector destroys anything that, that comes in contact with it, okay, in terms of vector spaces. But if we actually take the general matrix inversion problem and write it in its pieces, to get the inverse of a matrix in general, you need to compute something called the cofactor matrix, and you need to divide that by the determinant of the matrix. This is where going and reviewing a linear algebra textbook is handy. Because in general, you have to calculate this thing called the cofactor, which involves eliminating rows and columns and then doing some algebra, eliminating other rows and columns and doing some algebra. It's a mess, okay? That's why unitarity is so nice. But here, we actually don't have to focus so much on the cofactor matrix. We can just focus on the determinant. Because this is a non-trivial vector, this isn't just the null vector, okay? Because this is in general a non-trivial vector, and because in general this has a, how do I say this? This is a finite, okay, operator quantity here. The cofactor matrix will also be finite. But the only way to get the null vector acted on by something giving you a non-null vector is if the denominator of this equation is infinite. And the only way to get that to happen is if the determinant is 0. Okay? So assuming that this thing up here is a finite matrix, then all you have to do is figure out under what condition the denominator of this equation gives you infinity, so that you get a finite result on the left side. And the way to do that, of course, is to set the determinant equal to 0. So fundamentally, the eigenvalue problem boils down to this. You're going to find the A's such that the determinant of A minus little a times the identity matrix is equal to 0. All right, the determinant is a number, and you just need to write down the equations for the determinant of that matrix and set the determinant equal to 0 and solve for the A's. That's really what the eigenvalue problem boils down to. Once you have the A's, to get the eigenvectors, you go back and you write down A acting on V1 equals A1 V1. A acting on V2 equals A2 V2, etc. Using the A's that you figured out from the first step. Solve those equations for the vectors. All right, so first you're solving this equation for numbers, then you're taking those numbers and putting them into these equations to get the forms of the vectors. This requires a bit of art, because what you'll see is that sometimes as you're working on these problems, you'll get relationships between the elements of the vectors on the left and right hand side that are trivial. You know, you'll get something like the second component of V1 equals the second component of V1, which is a trivial equation. What that means is you can pick the number that you stick in there. So usually I pick 1. 1 equals 1 is a nice simple number to work with. In the end, you wind up having to normalize these vectors that you get. So you get a nice orthonormal set, or a nice normal set of eigenvectors out of this. And that will take care of any lingering, non-unit length that's present in the vector. All right. So let's do a simple example. Let me show you a simple example here. All right. So let's consider a 2D space. All right. So we have X and Y. And I've got a rotation matrix in this space, R2. Its action is to take X and rotate it into Y, and to take Y and rotate it into negative X. And so you can solve this and figure out what are the matrix elements of this matrix. Let's see here.
Isn't there a negative?
Yeah, there should be a negative one. Let's see.
The bottom left.
Yes. There we go. Okay, so that probably propagates in a nasty way through the rest of this, but I think the answer still winds up being the same thing, so it doesn't matter. Okay. Now, the next thing you have to do is write down the eigenvalue equation for this. So R2 minus mi, where the m are the eigenvalues, acting on the eigenvalue equals the null vector. Okay? All right, and from over here, we know that we need to basically start by solving this. Okay, we need to solve that equation. So we can actually write that equation out. We have the determinant of 0, 1, minus 1, 0, minus, okay, and then we have mi, so this is just m, 0, 0, m, all right, and that has to be equal to 0. Okay, so we can keep going. Determinant of negative m, 1, and then, minus 1 and negative m. Okay, and then this is just going to be equal to the product of these diagonals minus the product of these diagonals. So it's going to be m squared minus minus 1, which is plus 1, equals 0.
Yeah,
It's
imaginary.
Mhm.
Since of the negative.
Yeah. Okay, so m is going to be equal to plus or minus I. right, so this continues to ripple through my notes. What I probably did wrong was I probably didn't pick my rotation matrix very intelligently. I probably should have had x go to y and y go to x, in which case then you get positive numbers, but oh well. This is an actual rotation matrix, so this is what makes sense. All right, so let's keep going. This will be as much a surprise. Yeah, reflection operator would have been better for this, but let's see. This will be as much a surprise to me as it is to you. Okay. All right.
Lecture on the fly.
Lecture on the fly. It's not the first time I've had to do this. All right, so now we have the eigenvalues. All right, so now we need the eigenvectors. And so we have two sets of equations that we have to solve for this. So let's pick one of the eigenvectors. Let's pick m equals plus I. In this case, again, we have R2 acting on this particular eigenvector, which we'll call V. Why not? Why be creative at this point? Is equal to I times V. All right, so now we got to figure out what are the components of V. There should be two of them. All right, well, again, we can write 0, 1, minus 1, 0, acting on V1 and V2 is equal to I, V1 and V2. All right, and then finally we get two sets of equations out of this. So we get that V2 equals I, V1, and negative V1 equals I, V2.
So now you pick one.
Right.
So V1 equals 1.
Right, okay. Right, so let's pick one. Let's say V1 equals 1. That sounds good. All right, so if V1 equals 1, then V2 equals I.
And if V1
Yes,
equals
yeah,
1,
that works.
V2 equals -1.
Yep. Okay, so that works. Great. All right, so we have our first eigenvector. We have V equals 1I. Now, let's get it to be unit in length. It may already be, but we can at least try to calculate it and see. So to get it to be unit in length, we want to change this by dividing by the length.
So it's root 2. It's 1 over root 2.
Yep. Okay, and there's our first normal eigenvector. Okay? All right, so rinse and repeat. Solve another equation. You'll get a 3 by 3 on the homework, although I promise I was merciful. All right? So here we have W equals negative I. W, so again, 0, 1, minus 1, 0. W1, W2 equals negative I. W1, W2. So we get W1 equals negative I W2, and negative W2 equals negative I W1. So you can cancel the minus signs on both sides of that equation. All right, what do you like?
Let's do
W1
W2.
equals 1.
I'm getting no consistency here. Who? All right, Ting Ting, what do you like? W1 equals 1. Okay, and so W2 equals minus I. Yeah. Otherwise, it would be a degenerate.
Yeah.
Right? Yeah, if we had gotten two of the same eigenvalues, then that definitely would have worked. But this one has to be different than the other eigenvalue because this vector has to be different than the other. So, what's that? It can't work? Let's see.
The second one is I times W1 equals W2.
Oh. Yeah, so does this actually return
No,
the
no,
same?
no, we did it wrong. You
Ah.
did the first part wrong.
What did I do wrong?
So
So the
the,
equation.
it's
Two is
W2
one.
equals negative I W1.
Ah,
You
yes.
did that part wrong.
W2 equals negative I. Okay, and then, oh,
W1.
David, W1.
Now you have 1 less.
Yeah,
Okay,
there
there we go. And the sky is blue and the universe is safe. That's good. Okay. And so the normalization actually works out to be exactly the same again on this one. 1 over root 2, 1 minus I. Okay? So, again, you have to slog through this in a methodical way. All right, last topic, and then we'll finish for today. The eigenvalue equation sort of gives us a handy thing right away. We can recognize a solution to a very specific question in all of this business, and that is, if you have an operator A, which we do, is there another matrix S whose action diagonalizes the matrix A. All right, so if I have an operator A, and it is multiplied by S, I get some, knew I was missing something. Is there a matrix or an operator with the form S that gives us another matrix, lambda, that's entirely diagonal? That is, there are only entries on the diagonal that are non-zero. All the other entries are 0 in that matrix. A nice feature about diagonal matrices, one of the things that makes this sort of nice, is that once you can establish that it's possible to diagonalize matrices, and you put them in that form, they commute automatically. Okay? So this is key for angular momentum, and again relates at a deep level to the Heisenberg uncertainty principle. But the Heisenberg uncertainty principle is basically a consequence, in a sense, of the fact that we're using vector spaces and operators in vector spaces to describe nature. And so you're kind of stuck at some point with features like the Heisenberg uncertainty principle. It's unavoidable. All right, so let's imagine that we have, in fact, that it is possible to construct something like this. It turns out that the eigenvectors are what help us here. So if we have the operator A times a matrix S, where the columns are eigenvectors of A. You'll see why this just gives you what you want. Okay? So we have A times a matrix whose columns are V1, V2, Vn. All right, and so you can think about what that's going to do. Basically, you're going to have this matrix. It's each row in the matrix will be multiplied by one of the eigenvectors. Okay, and what happens as a result of this is you wind up getting a. I'm going to write it here. You get back the matrix whose columns are eigenvectors, but multiplied by a diagonal matrix where on the diagonal you have the eigenvalues and off the diagonal everything is 0. Okay? And so this is exactly what we were looking for. Right? This is lambda. Okay? So the eigenvalue, the feature that there are vectors in the space that when acted on by the operator simply return a number times the vector allows you to find the matrix that, that's this, okay, this is S, that returns a diagonal matrix when it acts upon A. All right, and so if we just take this equation, all right, so we found it, right? A S equals S lambda. And so finally, if we multiply both sides by the inverse of S, we get exactly what we were looking for. Now, here's the key thing. Let's think about two operators, okay, A and B. So here. Okay, and let's assume that it's actually possible to diagonalize them using the same S. Okay, so it's possible to do this. All right, so let's assume that that's possible. So we have two operators, and they're both diagonalized by applying the exact same operator S to them. What's the consequence of that? All right, well, so what we find out is that we can write AB, the product of the two operators, can simply be written in terms of this expansion, okay, S, A, S, S minus 1, B, sorry, hang on a second. Yes, that's fine. Yeah. Okay, And so, what am I doing wrong here?
Should be
The
Nothing.
lambda's in the middle.
Oh, yeah.
Lambdas, but-
Sorry about that. Yep, thank you. Knew something didn't feel right.
There it is.
Okay, there we go. All right, so now as long as we preserve the order, we can group these
I think-
oper.
I think-
Yep.
Yeah,
Backwards.
sorry.
Yeah.
They're backwards. Should be S lambda S minus one. S
Or
lambda
if you
S.
switch back to
Oh,
the A's and B's.
yeah,
you'll
yeah, yeah,
find
yeah.
it out.
You're gonna get the same result.
Yeah, but I want to get it for the right reasons. Okay, there we go. Right, yeah, right. So that would be obtained by multiplying from the left by S here, which cancels that out and puts S over here, and then from the right by S, the inverse of S, which cancels that out and puts S minus 1 there. Okay.
Originally, how you had it with the A's and B's, it was the product of lambda 1 and lambda 2.
Right.
Right. All right, but this is actually what I wanted. So, okay, so having written the product that way, this product right here just returns the identity. So we have S lambda 1, lambda 2, S to the minus 1. And remember what I said about diagonal matrices, they always commute. Okay? So this is equivalent to S lambda 2, lambda 1, S to the minus 1. And then if you put back in S minus 1, S lambda 1, S to the minus 1, this is just equal to BA. Okay, so it seems like a trivial thing, but it's actually quite powerful because, as you'll see next time when we talk about the expectation value of operators and the variance of operators, if two matrices commute, if two operators commute in a vector space, it means that they share a common basis of eigenvectors. Remember, this matrix here, S, has columns that are eigenvectors. And if the columns are eigenvectors of A, and they also diagonalize B, then they're eigenvectors of B as well. And so the minute you know that you have two operators that commute, you know something very powerful physically about the system. You know that these two operators, which in quantum mechanics may represent two different measurements, share a common eigenbasis that describes them both. And so you are at that point able to write down a single set of vectors that diagonalizes both matrices and describes the whole system and all the measurements you can make with those two operators. Okay? So we'll pick this up on Thursday and then get into angular momentum. I suspect we'll probably get to spin on Tuesday, but I'll need to grind through some stuff with angular momentum because then spin will seem trivial by comparison. So, any questions?